My name is Nia Sample, and we're going to explain the process of using the nodal slide. Optical elements are diffraction limited, meaning that unlike presented in geometric optics, a beam coming from infinity will not create a perfect infinitesimally small image at the focal point. Instead, there is an airy disk, the size of which is determined by the wavelength of the light source and the angle at which the beam is converging. The actual diameter of the airy disk is defined by the angle of convergence multiplied by pi and divided by the wavelength of light. Another parameter affected by these is the numerical aperture, which is the sine of half the angle of convergence, or the diameter of the lens divided by twice the focal length. In certain systems, such as a DVD player, a high numerical aperture is desirable to image the smallest spot size in a very limited amount of space. In order to achieve this, one can use a very large diameter lens, which is not possible with mechanical constraints in a DVD player, so a very small focal length must be used. Measuring a very short focal length of the lens is difficult, but luckily we have the nodal slide to assist us. The measurements we take are simple: the first and second microscope position, the rear nodal point of the lens, the rear vertex of the lens, and, if you want to find the thickness, the front vertex of the lens. The general setup of the nodal slide consists of a diffuse light source, pinhole, collimating lens, test lens, and the nodal slide on a traveling rotational stage and microscope. For demonstration purposes, we use the laser light source, added two polarizers, and imaged using a microscope camera. Light must be collimated in the first part of the system so that the light incident on the lens is effectively a point source beginning at infinity. First, use the microscope to focus the image through the lens. Position the nodal slide over the axis of rotation. This is done by moving the lens stand back and forth on the nodal slide using the dial while rotating the slide back and forth. You will know this is achieved when the image of the pinhole does not move when you rotate the nodal slide from side to side. Record the position of the microscope and the lens, making sure to take into account the position of the traveling stage on the optical rail as well as the position of the lens holder on the nodal slide. Next, use the microscope to focus on the rear vertex of the lens. Position the rear vertex of the lens over the axis of rotation. As in the second step, you will know this is done when the image of the vertex does not move with the rotation of the stage. One trick to do this is to add a little dust onto the lens to give you something to focus on. Of course, with higher-end optical elements, you would not add dust onto the lens, but for basic experimental lab procedures, this is sometimes allowed. In this example, our first microscope position was 615.9 millimeters, the second position was 590.9 millimeters, the first nodal slide position was 65 millimeters, and the second was 64.15 millimeters. The back focal distance can be found as the difference between microscope positions. The distance between the vertex and nodal point is referred to as delta prime and may be negative dependent upon the shape of the lens. The back focal length is then calculated by subtracting delta prime from your back focal distance. Make sure to pay attention and adhere to your initial sign convention when finding this difference to ensure an accurate calculation. Oftentimes, you will end up subtracting a negative number and the effective focal length will be longer than the focal distance. For our calculations, we found a back focal distance of 25 millimeters, a delta prime of negative 0.85 millimeters, which yielded a focal length of 25.85 millimeters. This was only 0.19% larger than the known focal length of 25.8 millimeters.